Okay.
Thank you very much. Sorry again.
It's okay. So before I introduce the treatment for the imperfect case, I will just give a quickly review of the perfect case, because I will also use the principal idea of the, what I use in the perfect case to the imperfect case. Okay. For the perfect case, we have the stochastic master equation to describe the time evolution of the actual state of the system, and we choose the target state is one the state this subset. Okay. And our objective in the perfect case, the perfect case means we know exactly the initial state and each parameters, physical parameters. Okay. So in the objective, our objective here is to provide the sufficient conditions on the feedback controllers, ensuring the exponential stabilization toward the target state, or just the asymptotic stabilization toward the target state. And here, I gave the first hypothesis, the assumptions on the feedback controller. I call it H0. The U is C1, okay? This part is just to ensure the uniqueness and existence of the solution of stochastic master equation. And we suppose this function U, the feedback controller is just the real scalar function, the real scalar abundant function of the density operator. And we suppose the function equals to 0 at the target state and non-zero at the other eigenstate. Okay. And under these assumptions, our stochastic master equation has only one equilibrium. It's exactly our target state. And in order to show the strategy, in order to realize our objective, the strategies consist of 4 steps. The first one, I call that the reachability of the corresponding ordinary differential equation, which can be obtained just by some calculation from the stochastic master equation. Which means we want to show that the solution of the ordinary differential equation can enter any arbitrary neighborhood of the target state in finite time. And for this part, I separate to 2 cases. The first one is we suppose the target state is rho 0 or the rho 2j. I mean the rho 0 corresponds to the rho 0 is just something like that, 0, and the rho 2j, okay, like that, or the diagonal matrix. For this case, it's very easy. In fact, it's obvious, almost obvious to show the reachability of the target state. But for the other more general case, it's not so obvious, and we need some additional conditions on the feedback controller. I call that H2, okay, which means in this subspace, we need our feedback controller satisfies this inequality, okay, because the left-hand side is always positive. It's always positive, definitely on this subside. So we can always, there always exists the feedback controller satisfies this inequality. And just by applying the support theorem, we can show that the solution of the stochastic master equation entering this arbitrary neighborhood at time t is positive strictly. And the second step is we want to apply the Fehler continuity of the solution of the stochastic master equation, and also we have the compactness of the complement of the neighborhood of the target state. Then we can show the probability of the stopping time is finite almost surely. Okay, which means we can, for any initial state, the solution can always enter in arbitrary neighborhood of the target state in finite time almost surely. Then we can always enter in an arbitrary neighborhood of the target state. For the third step is we want to use the local Lyapunov argument to show the asymptotic stability of the target state. And we suppose there exists a candidate Lyapunov function. It's positive. And assert that the Lyapunov the infinitesimal generator of the Lyapunov function is negative in some neighborhood of the target state. And this function is bounded by a non-decreasing positive function of the distance from the actual state and the target state. And just by applying the strong Markov property, we can show that the target state is almost surely stable. And if, furthermore, if we have some, if our Lyapunov function have some exponential property, which means lim sup, the LV over V is bounded by some negative constant, and our Lyapunov function is equivalent to some distance between the actual state and the target state. By applying the strong Markov property, we can show that the target state is exponentially stable, almost surely. And in the end, I have given the two examples of the Lyapunov function. The first one is for this particular case, if the target state is the rho 0 or rho 2j. We choose this as our Lyapunov function. Okay. And if the feedback controller satisfies the H0 and H1 is this. If our feedback controller satisfies these two assumptions, we can show that for almost all initial states, which means except the target state is exponentially stable with the Lyapunov exponent smaller than or equal to negative eta m. And for the more general case, we choose this function as our candidate Lyapunov function. And we suppose the feedback controller satisfies these three conditions, okay? H1, H0, H1, H2. And for almost all initial state, which is positive definite, the target state is almost surely exponential stable with the Lyapunov exponent smaller than or equal to the negative eta m over 2. This is just a brief review of the last two courses. And next, I will show you the treatment for the imperfect case. In this case, we have always the rho n bar is our target state. Okay. And then this is our system, angular momentum system. And we use the rho to describe the actual state of the system. And the omega and m is corresponding the related parameters. And we suppose our system is undergoing the homodynamic detection, and eta describe the measurement efficiency belongs to the 0 and 1 interval. Okay. And output is the observation process. Because here we suppose we don't know the exact value of the parameters omega, m, and eta, and we don't know the initial state. Okay, we don't know the initial state, which means we can always obtain estimation of the actual state, denoted by the rho hat. But the rho hat t maybe is not equal to the rho t almost surely. So in order to describe the time evolution of the system, we have write these two equations, and we call these two equations the coupled system. The rho describes the actual state of the quantum system, and the rho hat is the estimated state. Okay. Then we have also three estimated parameters: omega hat, m hat, and eta hat. And for these two equations, they share the same observation process, the YT. They're the same process. And for the UT, for the U feedback controllers, it's a function of the rho hat. They're the same. Okay. So from the practical point of view, we know, which means in the real experiments, we cannot know the exact value of the parameters, and we don't know exact initial state. Okay, which means for this case, it's more interesting for the real experiments. So here our objective, control objective is we want to provide the sufficient conditions on the feedback controllers and the function of the rule head and a valid domain of the three physical parameters, which ensures our state, actual state and estimated state can converge to the target state exponentially or just asymptotically. Okay, and here is a reference for this approach. And firstly, we suppose our feedback controllers satisfies H0. Okay, H0, which means H0, which means the target state equal to 0 and the other eigenstates are non-zero. There exists an equilibrium of the coupled system. Okay, denoted by rho K, rho n bar. And there is only one equilibrium, is our desired target state, okay? Which means for the others, n minus one equilibrium is a bad equilibrium. So the first step, what we want to do is, we want to show the instability of the bad equilibrium. And in fact, we can show that this instability is exponential instability. The instability of the equilibrium, which means there exists some positive constant R such that for all initial state belongs to a neighborhood of such equilibrium. The neighborhood here is defined by the S is a state space of the density operator. Okay. For OK not equal to the n bar, and the solution of the coupled system access this neighborhood infinite time almost surely. And in order to show this, we also separated the two cases. The first one is, we suppose our target state is a particular space. The particular case is 0 and 2j. For this case, we need the assumptions. Our feedback controller satisfies H1, okay, which means the absolute value of the feedback controllers is bounded by this function. C is positive and M for some constant C and M. And the second is a general case. Here we give we need the H3, the hypostasis of the feedback controllers. And we suppose the feedback controller Euro hat equals to 0 for all rho hat in a sufficiently small neighborhood of the target state. Sufficiently small. Positive. Okay. This is the first step. We want to show the instability of the bad equilibrium. And the second step is the reachability. Of the corresponding the coupled ordinary differential equations. And for this part, we have also separated to two cases. The first one is the special case, which means for all rho 0, the initial state for the corresponding coupled ordinary differential equations except the some neighborhood of the target state and all the bad in equilibrium. And also on the some conditions of the estimated parameters, the m and the omegas, and also the assumptions of feedback control H0. Can show the solution of the coupled ordinary differential equations entering an arbitrary neighborhood of the target state. So sorry, maybe here's arbitrary neighborhood. Arbitrary neighborhood here for all R positive infinite time. In fact, for this part, the proof is exactly the same. It's not exactly the same. It's almost exactly the same as in the perfect case. Okay. So second is a general case. For this case, it's not so trivial, it's not so obvious. And here we suppose our initial state belongs to the S-terms product with the interior of the state space, which means interior, which means everything is positive, definitely. And also on the some conditions of the estimated state, estimated the parameters, and also the assumptions of the feedback controller H0 and H2. Okay. H2 is what we used here. in the perfect case, which is a sufficient condition to show the H2 is here, is a sufficient condition to show the reachability in the perfect case for the general case. Okay. And we suppose the H0 and H2. And then we can show the solution. The coupled ODEs can enter in the arbitrary neighborhood of the target state. Infinite time. Under these two results, just by applying support theorem and by the similar arguments, we can show the probability is strictly positive for all positive. Okay. And the third step, it's the same, in fact. And we just apply the failure continuity. And the solutions are the compactness of the complements of the sum neighborhood of all the equilibria or denote this space and the gamma R and bar. And this is a compact space. Okay. And just by applying the standard arguments in the diffusion process, one-dimensional diffusion process, we can show that the expectation of this integral from the zero integral from the 0 to this stopping time of the characteristic function is bounded by a constant k. Okay, and this stopping time is defined which means that the first time entering the neighborhood of this target state is bounded by the constant, the finite constant. Okay, and this is just a very standard argument. I will also give some reference for this part. For example, we can find this and just the application this argument in the nonlinear stochastic differential equation, the Baxandal. For the okay. And once we show this expectation is bounded by the constant k, and then we can show just by applying step one. By applying the step one. Step one is the instability. It's instability of the bad equilibrium. Because here we can always from this, this subspace is a compact, okay. So this part is a neighborhood of the bad equilibrium, and we can also show the instability of this part, which means we can always exit from this part infinite time. So this part, this result plus the first step, we can show the probability that the first exiting the neighborhood abundant the neighborhood the target state is finite almost surely. But for this part, it depends the target state. If the target state from 0 to j, we can show all zero initial state except the bad equilibrium. Show on bar, okay. And if for the more general case, -1, the initial state S. Okay. This is the third step. From now on, we can show that for the solution of the coupled system can always enter in the arbitrary neighborhood of the target state infinite time almost surely. For the fourth step is similar to the perfect case. Here we also use the local Lyapunov argument. Okay, and the first we suppose there exists the candidate Lyapunov function. Here the function of the row and the row head, which is positive, such that the infinitesimal generator is negative in some neighborhood of the target state, and for some are positive, and also this function is bounded by non-decreasing function the distance between the actual state and the target state. Okay, and also by the strong Markov property. We can show that the target state is almost surely asymptotic stable. And here we denote the distance between the actual state and the target state at the D, and the distance between the estimated state and the target state at the D hat, okay? And then if we, if we have the Lyapunov function with the exponential property, which means the lim sup of the LV over V bounded by some negative constant, and the Lyapunov function is also equivalent to the distance. Also the strong Markov property. And then we can show the target state is almost surely exponential stable, which means here we can give an estimation of the rate of the convergence to the target state. In the last step, we have given an explicit expression of the Lyapunov function for the target state onto ρ0 and ρ2j. And the design example in the Lyapunov function is in this form. Okay, and for the more general case, in this form. Okay. And next, just by applying the similar arguments, as in the perfect case. Perfect case. And we can also obtain the sufficient condition on the feedback controller. The sufficient on the feedback controller to ensure the exponential stability of the target state. And in fact, in the following, we can see that the feedback controllers in the perfect case also works in this imperfect case. Okay. So I already introduced the principal idea, the strategy in the imperfect case, the stabilization. We can see that there's only two steps is new. Okay. In the first step to show the instability. And this part, okay, in the reachability of the coupled ordinary differential equation. For the general case, it needs some new treatment, new approach. For the others, almost exactly the same things as in the perfect case. So I will not waste your time. I will just show the proof of the first step and the reachability of the general case. Okay. Okay, firstly, introduce some exponential instability. Of a bad equilibrium. K and not M bar. And the basic idea of the proving the instability comes from the approach of the Kaminsky. The approach of the Kaminsky, they find the proof of the Kaminsky to show to avoid the explosion of the solution of the stochastic differential equation. Okay, they try to find some function, some Lyapunov function, so that the infinitesimal generator of such function is bounded by some constant. So the most important is to construct such function. Okay, but how to construct such function in our case? The first idea in my mind is we can show that it's exponentially unstable, which means it can exit some neighborhood of the bad equilibrium exponentially. So we just calculate log of such function, then we can extract the Lyapunov exponent, and this is a constant. And this is a basic idea in my mind. Okay, so I will give some details also separate to the two cases. Sorry. For the two particular case. And we assume the initial state and not at the target state. Okay, of course the target state is equilibrium. And moreover, we suppose the assumptions of feedback controller H0 and H1 are satisfied. And we give the valid domain of the estimate constant. The n corresponds to the dimension of our system. Okay. And because we have this relation, the fixed angular momentum equals n minus 1 over 2. Okay, in this case, we have also the 2j. Then there always exists a constant positive, and such that for all rho 0 hat into a neighborhood of the bad equilibrium, the trajectories of the coupled system axis such neighborhood infinite time, almost assured. Okay, and just from this addition of on the estimated state, we know that if our dimension equals to 2, okay, it's always valid, right? Because if n equals to 2, which there is 0, and this is always positive. Sorry, this is always negative, this part. And n equal to 3 is also valid. N equals 2 is exact. It's just the spin-half system or the two-qubit system, the qubit system, sorry. The proof is also based on the Lyapunov argument. And we choose this function as our Lyapunov function. In fact, this function is only the function of estimated state, which means it's a function of the row head, only the row head. Okay. And the idea here to show the instability is, change the color. The idea is we want to show that the trees row head cannot equal to 1. Okay, which means if the row head cannot equal to the row n bar, and of course the coupled state cannot equal to the bad equilibrium, right? And from the H1, assumption H1, we can show that the feedback controller is bounded by this function. The V is our Lyapunov function, okay. The C is positive and M is some constant, positive constant larger than 1/2. And then we calculate the infinitesimal generator of this function. And we have some positive constant alpha absolute value of the function t. Okay. And where alpha is some constant positive, and sorry, and the t equals to rho hat. And then we calculate, we can see that here is LV and it's parenthesis and here is V, okay. So we can calculate the limit, sorry. V over V is larger than the constant C1. Okay. Okay, I will see that. If this rho and rho hat convert to the, sorry, mistake. Okay, the bad equilibrium, okay. We can see that the rho hat convert to the target state because the Lyapunov function is only the function of the rho hat. Then the first term convert to 0. And the trace rho hat, rho and bar convert to 1. This is a constant, and this term, we can see that the trace J0 convert to the J minus K, okay, because the rho convert to rho K. And the trace J0 and rho hat convert to the J minus n bar. And from this, we can see that the T is negative because the n bar is only the, here we only consider the special case, n bar equal to 0 or the 2j, the minimum or the maximum value. So the tk is negative if the n bar equal to 0 in some neighborhood. And the t is positive, and is 2j if we have such such condition of the atomic state under the conditions if j okay. And just by this calculation, we can obtain this C1 equals to the 4 eta m j minus 1 eta m, okay, which is always positive under such conditions. And then we calculate the log of the function because we want to extract the exponent. The v is just the function of the rho hat, okay. The j is the stochastic part of the stochastic master equation. Square. And then we calculate this part. We have already some estimation from the C1. Then we calculate the second part. And in fact, we can also obtain some estimation. This part. smaller than C2. C2. Okay. And then we calculate the inf LV is larger than the C1 minus C2. And in order to ensure such, in order to ensure the C1 minus C2 is strictly positive, we need another assumption. Change your color. 2G minus 1. Okay. So under these two assumptions, we can have this inequality, lim inf the L, we can obtain this inequality, okay, which means there exists, or in some neighborhood of the bad equilibrium, the infinitesimal generator of the log V is larger than the constant, sorry, 3. That in some neighborhood. Okay. And then we define the stopping time and the first exiting time from this neighborhood. Exiting time. BR rho K from bar. Just by applying the Ito's formula, we have log V larger V is 0 C3 expectation to door. Okay, because the function the V is always between 0 and 1, so the log is always negative. And of course, this part is always negative. So we have the expectation of the exiting time respondent okay, it's bounded by some constant positive. Okay, so it's done. And here we apply the Ito's formula on the log. In fact, we cannot use directly because there's always a singularity because the V equal to 0, some singularity, but it's no problem here because we can just, in the perfect case, we can show that V cannot equal to 1 in the finite time almost surely. So there's no problem to strand us to use the Ito's formula here. And next, I will show you the instability for the general case. For general case, we need some strong condition on the initial state. We suppose estimated state, initial state is always positive definite. And we need our feedback controller satisfies H0 and H3. H3 means the U equal to 0 in some smaller neighborhood. Okay, sufficiently small neighborhood of the target state. And the valid domain of the estimated state. will denote this encoded this relation and the star. Then exists R positive such that for all initial state from this neighborhood, okay, with the K, then the solutions of the couple system access the BR infinite time almost assured. And the proof is almost the same, but we need another Lyapunov function. What we showed for the particular case is we choose the Lyapunov function and the 1 minus treat row head row n bar. Okay, which means what we showed is we showed that the estimate state cannot equal to 1. Okay, but for the general case, this method doesn't work. We need some indirect Lyapunov function. What we choose, the function is the row head u k. Okay, and the k is the same k as here, which means we want to show that this Lyapunov function cannot equal to 0. If this cannot equal to 0, which means the row head cannot equal to row n bar, okay? Because the trace of the row head equal to 1. If this is not equal to, if at the kth element at the diagonal is not equal to 0, for the n bar is cannot equal to 1. Okay, because the trace row head equal to 1. And similarly, we calculate the length, the LV over V. We can show that it's bounded by a constant. And also we calculate soup. C2. K square. Well, there's two inequality. And we can show that under the relation star. Okay, it's here, the star. The C1 minus C2 over 2 is always strictly positive. So, and moreover, in the last course, we showed that the interior of the state space is always invariant, almost surely invariant. Then we can show that they exist. We just apply the Lyapunov function. Sorry, we just apply the Ito's formula on the log V. Okay, just by applying the similar arguments, we can show that they exist. The R positive and the constant positive T3 L log V larger than C3 positive in such neighborhood. Okay, and then we can show that we can always exit this neighborhood infinite time almost surely, just by applying similar arguments. Okay, so from now on we can we have already showed the instability of the solution, instability of the bad equilibria. And next step is to show the reachability. For the particular case, it's easy, okay? So I will just show you some more complicated case. The 2g minus 1. Firstly, we have the okay, I will give the corresponding ordinary differential equation by the smaller d choose z rho v. Okay. And next I will denote this equation, this formula at the big V. Okay, at the big VT. Big VT here. Where the VT belongs to the this V. This is a set of all piecewise constant function. Okay, this is all piecewise constant function from the R plus to R. And then we have the corresponding ordinary differential equation for the equation of the filter. VT here. Okay. Sorry. Rho v hat the VT. Okay. The VT are the same. And I'll give the result. Suppose H0, H2, and H3 are satisfied for the feedback controller. And furthermore, we have also a -1. Well, suppose our estimated state, our estimated parameters satisfy this two inequality. For all epsilon positive and for all initial state. There exists a time, finite time, and a control input, piecewise constant function, such that the solution of the coupled ordinary differential equations can enter such neighborhood. Infinite time, which means here we before sorry, before t, which is positive, or which is finite. Okay. And the proof consists of 3 steps. The first step is you want to show the feedback controller U equal to 0 is not invariant. Okay, for initial state positive, because here in the interior of the state space, so this is always positive. There exists the V. There exists a control input such that for step 1, for some t positive. And this is very easy. This is very easy to show because under the H0, we know that the U rho k are not equal to 0. Okay, the k not equal to n bar. So we can always find the V, the piecewise constant function and the control input to control our solution towards this part, toward some neighborhood of the bad equilibrium. So we can always show that there exists the control input V such that the feedback controller of the rho Vt are not equal to 0 for at some positive constant time. And what is interesting, just as in the perfect case, I have already shown you some proposition. If our feedback controller are not equal to 0, and immediately we can show that the solutions, the density operators can become positive strictly for after that time. Okay, for all s stronger than larger than t, this type 1. The step 2 is and show that there exists finite time t1. There also exists the piecewise constant function such that the rho v t1 can entering the neighborhood of the target state. Okay, and moreover, we show that the epsilon is smaller than the xi. Okay, the xi is appearing in the H3. It's appearing in the H3 of the feedback controllers, where we suppose the U equal to 0. Feedback controller is to 0 for all rho in the BC, the rho n bar. Okay, which means if our if the rho v hat T1 is in this neighborhood at the moment, the feedback controller equal to 0. Okay, and this we can show that we can say that for the step 1 and step 2, we only concentrate on the estimated state. Okay, so and the feedback controller is also the function of the estimated state, which means for the step 1 and step 2, the proof is exactly the same as the one in the perfect case. But the most difficult part is the feedback controller is just a function of the estimated state of the rho hat, but how to control the solution of the actual state of the rho. This is the most difficult part. The step 3 want to show that for any epsilon between the 0 and the xi correspond to the H3. Okay. And we show that there exists the positive time T2. Also exists the control input such that rho T at show V hat into the neighborhood of the target state with T bounded by T2. And the idea, I will give the basic idea for the proof of step 3 is first you want to show there exists the control input. Okay. And first you want to show that we focus on the estimated state, which can, because from the step 2 we know that it already entering such neighborhood B epsilon. And next we want to show that the solution of the rho V hat always remains in this neighborhood. Okay. In this neighborhood B epsilon. And at the meantime, the solution of the rho T of the actual state can enter in such neighborhood. Okay. And epsilon can be chosen arbitrarily. And this idea is inspired from the approach in the Tristan's paper. And Clément Becrini for the communication, mathematics, and physics. 14. Okay. So by the step 1 and the step 2, so that for OT larger than T1, the rho VT n-bar, which means the trace rho VT, the rho n-bar. Okay. The definition is strictly positive, and hat is also strictly positive. And then we define the FKT and the rho VT KK over rho VT n-bar. And we define the F hat KT and the rho VT hat KK T hat n-bar. Okay. And if our solution of the coupled system converge to the target state, which means this part convert to 1 and this part convert to 0, the similar to 1 convert to 0. Okay. And of course, we already saw that for after the time T1 is always positive. So for this 2 is well defined for this 2 to function. Then we calculated the derivative. In the first step, we want to show the rho VT always remain in this neighborhood. Okay. And next we show that at meantime, the rho VT, the actual state, can enter in such neighborhood. So firstly, we show that the estimated state can remain in that neighborhood. We just calculate the derivative of FKT. n-bar, okay. That is just some function, bounded function of the rho hat, okay, denoted by the theta n-bar hat, rho k. Sorry. No. plus. Okay. And moreover, if this control input satisfy this inequality, so eta n. Okay, denoted by the 2 star. For some constant alpha smaller than 1/2, then we can show that which improve this part is smaller than a positive negative, okay, denoted by the Cn bar hat, which equal to and moreover, we know that the U is continuous because it's C1, okay, so it's continuity. Due to the continuity of U, if let's just write there, due to the continuity, if the U and U equal to 0 from H3, U equal to 0 for all row head in epsilon rho n bar, C rho n bar, okay. This is for this part, it comes from the step 2. And we can show that for any V, T satisfies the 2 star inequality. And for the T in the T1, a small neighborhood is of the T1 with epsilon positive but sufficiently small, okay. And we have the U equal to 0, and then we have the derivative of IKT smaller than Cn bar epsilon FKT. Okay. So just by Grunwald inequality, we have FKT smaller than, sorry, error hit. Okay. Here is okay. Smaller than FK0 hit E exponential Cn bar T. Then we just calculate the sum, the rho V T n bar, sorry. Okay, the rho V T. This is exactly the sum of the K number, the FKT, okay? Sorry, the FKT, because our FKT definition of FKT is this one, okay? The rho KK over the rho n bar. So we do the sum over all the K do not equal to the n bar is exactly this term, smaller than, due to this inequality, okay? It's smaller than n bar hat T. So K0. which is smaller than, because this, of course, for the Cn is positive, smaller or equal to than 1, okay, but it is smaller exactly than 1. So we can show that this is rho v0 hat and bar, rho v0 hat and bar, okay. So we have this is smaller than this strictly, which means the rho vt hat and bar is larger strictly than rho v0 hat and bar, okay? Which means the rho vt stays in such neighborhood, right? And moreover, we know that the u is always equal to 0. And as t tends to infinity, converge to the rho n bar. Okay, and this is very important for us. The u will remain 0, but keep the 0. Okay, so we do the exact same calculation for the fkt. So we suppose for t larger than t1 and the k to not. FKT. So from now on, we focus on the actual state. And if we t satisfies the 2 star is the condition here, which guarantee that this part is always bounded by a negative constant. Okay, satisfy this 2 star, and this inequality for some constant beta smaller than 1/2. I call that the 3 star, and the 3 star can show that this part is bounded by a Cn bar. Okay, the positive constant, the negative constant R beta strictly negative. And for the star and 2 star, which can be guaranteed by the inequality star. Okay, which can be counted by this inequality. And then just by applying the similar arguments, we have smaller than Cm fkt, right? The Grunwald inequality Cm t. Okay, which means the rho vt for the actual state will also converge to the target state when t goes to infinity. And okay. And this is for the reachability, which means I will just another 3 minutes, I will give the final result for these 2 special cases. Okay. If our target state, it's the particular case, and for all initial state, And we suppose H0, H1 are satisfied for the feedback controllers. And also the estimated state, estimated parameters is bounded by this inequality. The target state is almost surely exponential stable with the Lyapunov exponent less than or equal to So just consider some particular case. If the eta m equals to the eta hat, if we have the eta m hat, which means if we know exactly the estimated state, in this case, this is exactly the result in the perfect case, okay? Sorry. And for the general case, consider only the interior of the state space. And here we suppose the feedback controller satisfied H0, H2, and H3. And also the estimate state satisfy these two conditions. If m bar equals to j. And if not, if m bar are not equal to j, okay, where L m bar equals defined by this constant, minus m bar, okay, then the target state almost surely exponential stable with the Lyapunov exponent smaller than or equal to okay. And just by the similar discussion, if we know exactly the parameters, which means the eta m hat m hat equal to eta m, we can show that this, sorry, there's negative, is equal to the eta m over 2. It's also exact value as in the perfect case. Okay, I think we can stop here.
Okay, thank you very much, Weichao. Are there any questions?
Yeah, thank you, Weichao. So yeah, so Armand, do you have questions?
I have in fact two questions.
Yeah.
These two conditions you wrote in the for these two final results. So do they mean that you are in a kind of perturbative regimes when you want this eta to be close to eta hat to be close to eta, or not exactly? I mean, I really don't have any intuition about that. So does it mean that it's not too far or not? It is not that condition.
Yeah, because the problem is the eta. In fact, Okay. In fact, these two, the eta without head, the eta and n is actual for the real system. It's some constant for the real system. And for me, from the practical view, we cannot know the exact value for these two parts. So if we don't know the exact value, we cannot to give the exact estimation. This is the problem. So we want to find some, is it possible to relax the condition? Which means if we don't know the exact value, is it possible to find some condition on the feedback controller to control the system? So what I did is we can relax a little bit, which means for the estimated the parameters, it's not need to equal to the exact value of the real parameters. Maybe exists some errors, it's no problem. We can also obtain the Lyapunov exponent, which means that the system will also converge exponentially to the target state. But also, which means it depends on, in fact, it depends. If we have another some conditions, more stronger restriction on the initial state, we can also relax. We can also, which means we can also obtain some more good estimation of the target of the parameters. Okay, which means the errors is a little bit bigger is no problem, but it depends the Lyapunov function. And I have did some assumptions discussion on this part in the paper.
Okay. So when these conditions are not satisfied,
this is only the sufficient conditions.
Only sufficient conditions.
It's not the necessary.
Okay. And the second question is about your system. Well, these two results concern the case when you do have this feedback control, right? In your equation. So if you don't have your feedback control, what? I mean, you state something. I think you had some results also in that case, right? So what can you do in the system?
Yeah. In fact, but I didn't discuss. For that case, we suppose we have we know exact value. Okay, we suppose we know the exact parameters, which means for the eta equals to the eta hat, we can obtain the perfect estimation for the parameters. And sorry, okay. Wait a moment. Okay, perfect case. Sorry, imperfect case. Okay, it's here. So we can show that if the u equal to 0 identically, right? What do you mean? Okay, and the rho t and the rho t hat will converge. Normally, in that case, we have normally in this case we have the n square equilibrium, right? We have n square equilibrium, but we can show that it will converge to the rho n, and for this side, for the n equal to the 0 to 2j. Okay.
It converges to the union of the other states, or
the union, which means the rho 0 or until to the rho 2j, with a certain probability. We call that the quantum state reduction.
All right, but you still have a stochastic system, right? You're still
always did this
so,
part. In fact,
well, this is about point-wise convergence, right? So you consider convergence of trajectories. So if you relax a little bit and you consider convergence in low,
sorry, there.
If you consider convergence in low, I mean convergence in probability or convergence in just a convergence of lows.
Okay.
Is it possible to say something more about that or not? It's I mean, because
what do you mean the more about that?
No, I mean you have convergence about to some set, right? So for almost surely your trajectory converges to a set, which means that the distance between. Although I don't see how can it be. Yeah, but then this means that at some point you enter the neighborhood of one of them and you stay there, right, or not?
Yeah. For example, these are equilibrium. Each point are equilibrium. If we stay here, we will stay here. We cannot move. But what I mean, the problem is, sorry, not the problem. The result is, if we start with any other initial conditions, we can always convert to this part. And from the Tristan's paper, they also give some estimation of the rate of the convergence. But for each part, each state, we have the different probability, and each probability of the convergence depends on the initial conditions.
Okay.
So what I did here is just we control the probability, which means, for example, if u equal to 0, for example, maybe we convert to this part with the probability 30%, maybe, for example. But what we want to do is if we choose this as our target state, we want this probability equal to 1. Okay, for the other equal to 0. This is what I did.
Mhm.
Which means we control the probability.
Okay. Are there other questions? Okay, so if there are no more questions, then maybe I should stop recording.
Okay.